Hello, geometry students. We are now going to prove the Pythagorean Theorem, one of the most famous and most useful theorems in all of mathematics. So this is used a lot in middle school and high school in trigonometry, and this is going to be a proof of it. Now, there's lots of proofs of this. There are literally more than 100 different ways to prove this, but we're going to do, in this video, I'm going to show you how to do this using the area method. So the problem is well stated. It says given a triangle, a right triangle with lengths A, B, and C, and we want to show that A squared plus B squared has to be equal to C squared. And like I said, we're going to do this using area. So my first step is to construct four congruent copies of the given triangle. And the reason that we can do this is the ruler postulate and the protractor postulate, which says that I can construct any length that I'm given and any angle that I'm given. So I'm going to construct four congruent copies, and I'm going to align them in this manner. So let me finish drawing my square here. So I'm going to call this B, this is going to be A, this is B, this is A, this is A, this is B, this is B, this is A, and this is how the triangles are going to be formed. Okay, and so the four copies of them are here. Okay. And there we go. Okay, so I've made four copies of the same triangle, and I've aligned it in this way. And you can see that the big part right here, the entire outline of these four triangles now form a square. And my goal is to somehow show that A squared plus B squared is going to be C squared. And by the way, all of these lengths that are on the inside here is going to be C. Okay. So I'm going to name these corners here just so that it's easier for us. Okay, so I'm going to name these geometric figures here so it's a little bit easier for us to talk about. So I'm going to name these corners X, Y, or W, X, Y, and Z. Okay? So I have a square called W, X, Y, Z. So in my next statement, what I'm going to try to show is that the inner whole here, made of these three sides, C, 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 and C, that this actually is a square as well. Okay? Now you can see that it's already fulfilled one of the requirements of a square. Everything is the same length, but these angles I also have to show that they're 90 degrees. Okay, and this isn't too hard to show. So I'm going to name some another set of angles here. So I'm going to call this here angle 1, this here angle 2, and this here angle 3. And if you can see here that I'll name one more angle down here. I'll call this angle 4. Okay. And so from this we can see that angles 1 and 4 are congruent because they're reflexive. We made them that way. Or really it's CPCT. This triangle up here and this triangle here that's sort of tall, okay, is the same triangle. We made 4 exact copies. So I can say that the measure of angle 1 is equal to the measure of angle 4, and this is really CPCT, or congruent parts, corresponding parts of congruent triangles. And then you can also see here that angle 3 and angle 4 have to add up to 90 degrees. So the measure of angle 3 plus the measure of angle 4 have to equal 90 degrees. Because I have an angle here that's 90, all three of these have to add up to 180, so 3 and 4 have to give you 90. And that's the triangle sum theorem. And I'm going to substitute 1 in for 4. So measure of angle 3 plus the measure of angle 1 is equal to 90 degrees. So this is substitution. Also, 1, 2, and 3 have to be 180 degrees. So the measure of angle 3 plus the measure of angle 1 plus the measure of angle 2 have to equal 90 degrees. Okay? And this is angle addition. You have one angle here, another angle here, another angle here, and they all form a straight line. So that's got to be 180 degrees. So this is angle addition. Angle addition postulate. But 1 and 3 make 90 degrees. So 90 plus the measure of angle 2 equals, 180. I don't know why I wrote 90 up here. So this should be 180 up here. This would be 180. Okay. And this is substitution. And finally, I can subtract 90 from both sides. And you can see now that measure of angle 2 is equal to 90 degrees. Okay. So this is the subtraction property. Let me move this up here. Okay. So this square here, and let me name this square as well. So I already used WXYZ. Let's call this JKLM. So if we just repeat steps 3 through 7, you can see that all of these angles in here, so angle 2 is 90 degrees, and we can repeat the exact same proof again and again, here, here, and here, to show that those three angles. But for the sake of brevity, we're not going to repeat that. So now we can say that JKLM is a square. And this is the definition of the square. They're congruent sides and 90-degree angles. So as we continue this proof here, I told you at the start that this is really a proof by area, and in fact it is. But we've taken a little bit of a detour here, and all this stuff in blue is done to show that the inner, or the white figure right here, is also a square. So now we have two squares, the square WXYZ and the square JKLM. Okay, now I'm going to in fact use the area of these to show that a squared plus b squared equals c squared. Okay, so what step are we on? We're on step 9. Okay. So now I can show that the area of WXYZ is equal to a plus b squared, because that's the definition of the area of a square. Okay. So this is the formula for the area of a square. And I can also say this in another way, that the area of WXYZ is equal to the area of JKLM plus 4 times this triangle, these triangles right here. So I can show, so the square WXYZ, the big square here, that total area is really the area of this white square added to the 4 triangles here. So there's another way that I can say this. This is the area of JKLM plus 4 times the area of triangles, of the right triangle that I made, because I got 4 of them here. Okay. So now we can use the transitive property and set these two equal to each other. So I can say a plus b squared is equal to the area of JKLM plus 4 times the area of the triangle. Okay. And then we'll just apply, do a little bit of substitution here. So the area, so I got A plus B squared is equal to, now the area of JKLM, that's really C squared. It's just one side times another side. Okay, so this area here is just C squared plus 4 times the area of the triangle. Well, this is really 1/2. The base of the triangle here is B, and the height of the triangle is A. So times B times A. Okay. And then we do a little bit of algebra. So I'm going to cover this up here, so I have enough space to do my algebra. So this is really A plus B times A plus B. Be careful, it's very tempting just to say it's A squared plus B squared, but that's not really true. And I'll simplify over here. This is C squared plus 2AB. We got to FOIL this, so this gives us A squared plus B plus AB plus AB plus B squared equals C squared plus 2AB. These two terms combine, and you have A squared plus 2AB plus B squared equals what we have on the right hand side. And you can see that we can subtract 2AB from both sides, which leaves us with A squared plus B squared equals C squared. And there we have it. We've completed our proof. This is fairly a lengthy proof. It involves 16 steps, but really 8 of those steps, or 7 of those steps, is kind of a detour here for us to show that this white figure right here is in fact a square. And then the other steps down here is a lot of algebra. It's knowing how to use the distributive property and foiling. And once we've done all of that, we succeeded in showing that if you have a right triangle with the lengths A, B, and C, then A squared plus B squared equals C squared, provided that C is the hypotenuse. Later on, we're going to see another proof of the Pythagorean theorem that doesn't use area at all, and in fact uses similar right triangles.